important conclusion. Now let's go on to the next important experiment that was done. It was done by a French scientist named Jacques Charles, and there's his name. He lived from 1746 to 1823. So you see, all these experiments were done hundreds of years ago. So I don't know what equipment they used, but they did a good job because we're still using these laws today. So what I'm doing is I'm trying to show you where PV equals nRT comes from. If you break it down into simpler situations, you come up with these cases I'm discussing. This particular one is called Charles' law, but it really is the relationship between volume and temperature of an ideal gas. So remember, we're talking about gases that are around room temperature, 25 C, and around 1 atmosphere pressure. So in this case, we also have a closed container, but in this case, instead of constant temperature, we're at constant pressure. So you recall Boyle's law was under constant temperature. But the amount of gas is a constant. It doesn't change. So if pressure and N are constant, and you rearrange the ideal gas law, you come up with NR over P is a constant. And therefore, if you put everything else that's part of the ideal gas law on the other side, that would be V over T. So V over T, this again, in every case I'm discussing, if you look carefully, you'll just see that what I've written here at the top is just a rearranged ideal gas law, where I'm putting the variables, the things that can change on one side, and the things that are being held constant on the other. So again, a constant, what I mean by that is it's just a number. We don't care what the number is. All that matters is that it doesn't change. Therefore, we conclude that V over T, when you do hold pressure and amount of gas constant, the V over T ratio will always be the same. So we can say we can have two conditions. Condition 1, the initial, condition 2, the final. They'll always be equal to each other. An illustration of that would be pouring liquid nitrogen on an air-filled balloon. I'm going to try to insert some YouTube videos into some of these discussions, and I'll try it right now. So if you do see the video, you'll see that when you pour a liquid nitrogen, which is extremely cold at 77 Kelvin, absolute zero, the coldest temperature possible is 0 Kelvin. So liquid nitrogen, very, very cold stuff, 77 Kelvin. But it's pretty cool. You pour it over an air-filled balloon, and the balloon essentially collapses to nothing. That's an illustration of Charles' law. So how do we do that mathematically? Let's say I said, give you an initial volume of a balloon, about 2 liters, like a volume of a 2-liter bottle of Pepsi or soda that you buy at the supermarket. Let's say we're at room temperature, which is about 293 Kelvin, is about room temperature, 20 degrees Celsius. Remember, you have to use temperature in Kelvin. We will most commonly use liters for volume, but we can use milliliters too. But let's say you have a balloon at room temperature around 2 liters. You pour some liquid nitrogen over it. What would the volume be? Well, you know it's going to shrink. V2 should be smaller. So when you're doing these problems, you should always predict what you're going to observe. Is the pressure, volume, temperature, whatever, is it going to go up? Is it going to go down? Is it not going to change? Have a general estimate in your mind, and then once you get your answer from your calculator, does it make sense to you? If it doesn't, then go back and check and see where an error might have been made. But in this case, if you just rearrange this equation, what we're solving for is V2. So again, I cannot stress enough how your basic algebra skills are key here. You must be able to solve these equations. V2 is equal to V1, which I've written here, times if I just move the T2 over to the other side, I get this equation. V2 equals V1 times T2 over T1. T2 is my new temperature, my low temperature. T1 is my higher temperature, my room temperature. As you can see, it's just multiplying the initial volume by a number that's less than 1. So that would mean that the volume that I calculate is going to be lower, which makes sense. I do predict that the volume I'm going to get should decrease, and it does. It goes down to about, according to this law, about 0.53 liters. So its size shrinks about 4 times. So the conclusion I draw is that volume and temperature are directly proportional. It doesn't look like it from this equation, but when variables are directly proportional, they're actually divided by each other. If you look back at Boyle's law, these variables, where was that? Hold on one second. Boyle's law looked like this. These are inversely related variables. P and V are inversely related, but they're multiplied by each other. Okay, that's not sometimes throws students off a little bit. So when variables are divided by each other, it means they're directly proportional. And graphically, we can represent Charles' law like this. You graph volume on the y-axis versus temperature. We could express temperature in degrees Celsius or Kelvin. I've shown you here in degrees Celsius. But if you collect data, V over T data, for different situations, which is what we're going to do in this week's lab. I'll show you some sample data, but it should look something like this. If we can't measure anything below, real cold, maybe to about 77 Kelvin if I had liquid nitrogen, but I don't. But if I measured around room temperature, I could do what's called extrapolate the data. So that's why I've drawn the line. The solid line means I've actually collected data. That's real data. But I'm assuming that the gas is going to behave all the way down to 0, very cold temperature. I'll assume it will behave the same way. So I draw that as a dotted line. It's called extrapolation. If I do that and I have good data, I should get my line crossing pretty darn close to negative 273.15 degrees C. If I do, that means I did a very good experiment. I am predicting that at 0 temperature, the volume of the container should collapse to 0. Now in reality, if you cool a gas down to this cold of a temperature, somewhere in here, it's probably going to liquefy. That's why nitrogen and oxygen, when you cool them, you get liquid nitrogen and liquid oxygen. Things will condense into liquids long before they collapse to 0 volume. So that's a very important result called Charles' law. So keep that in mind. The third famous experiment, okay, make sure you can see that, that's good. I don't know if it's in focus here. Let's focus that, sorry about that. If the last slide was out of focus, I apologize for that. So this third situation is, and I just noticed that should write that there, sorry there, that's N. So this is a closed container again, but now we're at constant volume, and the amount of gas is constant. So now we've had a situation where temperature is constant, pressure was constant, now volume is a constant. So if we rearrange PV equals nRT and we put the constants N and V on one side of the equation and R is a constant, so it's always going to be on that side, we get this situation. Now we have, instead of V over T, we have P over T is a constant. So that means any situation now, if I have constant volume and constant amount of gas, the P over T ratio will always be the same. So P1 over T1 equals P2 over T2. That's called Gay-Lussac's law. He was another French scientist that lived from 1778 to 1850. So what are some real-world applications of this law? Well, if you ever have spray paint or any aerosol can, if you read carefully, it says don't throw in a fire even when it's empty. That's why, because gases are going to behave according to this law. If you raise the temperature of a gas, the pressure is going to rise to dangerous levels. That's what this law is saying. As temperature rises, molecules are going to move faster, therefore they hit the walls of the container with more force, therefore the pressure goes up. the volume of the container is constant in this case, so the can cannot expand to accommodate the higher pressure. Not like an air-filled balloon or a hot air balloon, which could do that. This can't. A metal container cannot expand its volume. It's constant. There's also a video I'm going to try to insert at this point, which is called the collapsing can. It's a very cool demonstration to show you the power of atmospheric pressure.
Closer and closer and closer, and you can hear the can starting to crinkle just a little bit. It's crinkling. It's even talking to you. The hard part is, you have no idea. Bam! That was a good one, all right? Isn't that awesome? Bam! That's how to crush the can.
So, assuming you've seen that video, you can see how powerful the air pressure around us is. If you lower the pressure inside of even a metal drum, you can use the power of the air pressure to crush that metal can. We can also do that experiment with aluminum Coke cans and cans of soda, and I might show you that on another video. But there's lots of YouTube videos you can see that demonstrate that. A practical calculation we can do illustrating Gay-Lussac's law would be this one. Think of a car tire. Here's our little gauge. When you measure the gauge pressure on a tire, you probably didn't think about it, but if the pressure you're measuring is actually higher, it's the amount above atmospheric pressure that's inside the tire. That's why we call it gauge pressure. The pressure inside the tire is actually higher than the gauge pressure is showing you. The gauge pressure is just taking atmospheric pressure into account. So let me show you how that works. Let's say today, for instance, or in the middle of winter, you're measuring the temperature of the pressure of your tire, it's 32 degrees Fahrenheit, the freezing point of water. You fill the tire and it says 35 psi, 35 pounds per square inch. Let's say you drove to Florida, or all of a sudden we had a heat wave the next day, and the temperature outside was 80 degrees Fahrenheit. What would the new pressure be? How would you calculate that? So when you're doing problems in the textbook, it's always helpful to write down all your variables. Make a little table if you have to. But you should be able to read the question and see, oh, I need to use Boyle's law or Charles' law or this one, Gay-Lussac's law. In this case, I would use this one because I'm given two different temperatures and a pressure, and I'm asked about a new pressure. So if you think about it, a tire is a constant volume situation. The tire maybe flexes a little bit, but it's essentially a constant volume system, and the amount of air inside we'll assume is a constant. So how would you do this problem? How would you calculate the new pressure? Well, we're going to calculate P sub 2. Think of it that way. The new pressure you're calculating, the final pressure, if you want to call it that, is P sub 2. But first we should do some conversions. Now, after I did this on this handout here, I realized I didn't necessarily need to convert pounds per square inch to atmospheres, but since I want to stress that atmosphere is our unit that we prefer, I converted the initial pressure of the tire, 35 psi, to atmospheres. I wouldn't expect you to know this, but 1 atmosphere pressure is equal to 14.7 pounds per square inch. So if you take 35 psi and convert it to atmospheres, it's about 2.4 atmospheres. What that means is, assuming that outside pressure that we experience is 1 atmosphere, it means the pressure inside the tire is actually 3.4 atmospheres. When you put the gauge on the valve of the tire, the inside of the tire is pushing against atmospheric pressure, which you would measure as the difference. So you'd measure 2.4 atmospheres. But we do need to convert 32 degrees Fahrenheit to Kelvin. So 32 degrees Fahrenheit is 0 degrees Celsius, which is 273 Kelvin. Notice this is my initial temperature, which I'm calling T1, T sub 1. And this new higher temperature, 80 degrees Fahrenheit, is my T sub 2. So if you look at this equation, I'm solving for P sub 2. So P2 is equal to P1, move the T2 to the other side. So it's P2 equals P1 times T2 over T1. If you can't see that, do on your own the algebra and make sure you can manipulate these equations, but this is what you'd get. So you plug in, and again, usually here in this case we have 4 variables, 4 possible unknowns. I give you 3 of the 4. You plug them in, and you get your answer. The initial pressure is going to go up. We know the pressure is going to go up, so it makes sense that we multiply the initial pressure by a number greater than 1. That's the only way we can get a pressure, P sub 2, that's higher than the initial pressure. And it goes up to 2.6 atmospheres according to this law, which if I convert back to PSI is 38 PSI. So the amount of pressure increase is not dramatic. It's noticeable, but it's not going to cause your tire to all of a sudden fail on you. There are other factors. This is a greatly simplified situation, but for the most part it allows pretty close predictions to what's true. The conclusion we would draw from this, like we did for Charles' law, is that pressure and temperature are directly proportional. So we can make a graph like this. Let me make sure that's clear here. Is that in focus? I believe it is. Pressure and temperature are directly proportional. So if you extrapolate from down to 0 temperature, the pressure, in theory, all molecular motion would stop. So the pressure should go to 0 as well. The last important law that led to the ideal gas law was, I'm not going to go through in such a detailed analysis as I've done for the other 3. It's called Avogadro's law. You might recognize his name, Avogadro's number, the Italian scientist who lived from 1776 to 1856. He said that he noticed that equal volumes of different gases at the same temperature and pressure contain the same number of molecules. So he did work that dealt with numbers of molecules, which is Avogadro's number of molecules per mole. That's why they call this Avogadro's law. I think of all of them, it's the easiest one to understand. It's the most obvious. But his work led to a very important conclusion or observation. At standard temperature and pressure, STP, any gas, it doesn't matter what it is, any gas occupies a volume of 22.4 liters per 1 mole. So an illustration of Avogadro's law is just simply blowing up a balloon. You blow air into a balloon, the amount of gas goes up, N is air molecules. The more air you blow in, the N goes up, so the volume goes up. They're directly proportional. So what this also allowed us, as I said, was it allowed us to calculate the volume of a gas at standard temperature and pressure. We often pick a case of in a scientific formula where we have a set of standard conditions that we can relate everything to. For gases, it's standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere pressure. Well, now you can use the ideal gas law, and I can prove to you that at STP, any gas occupies this volume of 22.4 liters. So if you go back to the ideal gas law, P equals nRT, solve it for volume. What would be the volume of 1 mole of gas at standard temperature, which is 0 degrees C, but remember we must use Kelvin. 0 degrees Celsius is 273.15 Kelvin, and 1 atmosphere pressure. You plug those in, you get 22.4 liters if you round to 3 sig figs. That's a very important result. 22.4 liters is about the size of a box that's 11 inches on a side. Okay, so 11 inches, 11 inches, 11 inches. It's not terribly large, but if you have any gas, it doesn't matter if it's oxygen, nitrogen, carbon dioxide, if they're all under the conditions of 1 atmosphere and 0 degrees Celsius, which is this much Kelvin, you would have a volume pretty darn close or exactly equal to 22.4 liters. So that allowed scientists to actually carry out chemical reactions with gases by simply measuring the volume. They didn't have to weigh the gases. They could just use volume and relate that to numbers of molecules. I actually forgot, there is a 5th gas law or simplification of the ideal gas law called the combined gas law. It just is using some math. It takes the three laws we've just discussed. Boyle's law, volume and pressure are inversely proportional. Charles' law, volume and temperature are directly proportional. And Gay-Lussac's law, pressure and temperature are directly proportional. And it combines them into one law. If you do that, you get PV over T is a constant for a situation in which you have a constant amount of gas. There are some practical examples of that. I want to show you here a calculation with that. Like a hot air balloon would be a situation in which you'd have the only thing that's a constant is the amount of gas inside the balloon. But if you rewrite PV over T for two situations, you get what looks like a complicated equation, but it isn't. It says P1 V1 over T1 equals P2 V2 over T2. It just means that the PV over T is always going to be a constant for any situation. So here's a real practical application of that law. So let's say we give you a situation in which you have a helium-filled balloon that they use to carry scientific instruments into the atmosphere. These balloons are huge, not so much at sea level, but when they rise into the upper atmosphere, they are gigantic. There's a really cool video, I just thought of it, where you might have seen the world record jump from altitude. It was sponsored by, I believe, Red Bull, but he was carried to, I believe, over 104,000 feet. He could actually see the curvature of the Earth. It's a really cool video. You should watch it. But you notice when they will show you that video that the volume of the balloon that carries them to that great height at the sea level is drastically smaller than when it is up high in the atmosphere. And that's a consequence of this combined gas law. It allows us to calculate what the volume would be. So here's how you do it. Just like the others, you have a set of initial conditions, and you're asked to calculate a final condition. So suppose we launch this balloon at ground temperature. At the ground, temperature is around 22.5 degrees Celsius. Pressure is around 1 atmosphere. It's a little low for that day. Let's say it's 754 millimeters of mercury. 1 atmosphere pressure is 760 millimeters of mercury. So a little bit of like a cloudy day would be, a little low pressure would be a little bit lower than 760. So that's totally fine. Let's say the initial volume of the balloon is still large, 4,190 liters. What will be its volume as it rises to 20 miles up? Now, altitude is not part of the equation, but at that high altitude, if you've ever traveled high up into the Rocky Mountains or any mountain range, you know it gets very cold at high altitude. That's because the air is less dense up there, so the temperature drops. It'll be very cold, negative 33 degrees C, let's say, at the high altitude, and the pressure will be very low. It drops by a factor of 10, down to 76 millimeters of mercury. Let's assume no gas escapes from this helium-filled balloon. What would be the volume up at the altitude of 20 miles? So this is where you'd have a situation in which you'd use this equation. Now we're solving for V2. But in this, when I show you my solution here, I'm calling that V sub F, V final. So the subscript 2 is final condition, subscript 1 is initial condition. If I solve this equation for V2, I get this. Make sure you can derive this yourself. Okay, I've just rearranged the variables. I've written them like this to show you that the final volume is just the initial volume times a couple of factors. The ratio of the initial and final pressure times the ratio of the final and initial temperature. And that should make sense because pressure and volume are inversely related. So I have the initial on the top and the final on the bottom. Volume and temperature are directly proportional. That's why I have it like this. So the pressure dropping is going to cause my balloon to go, the volume to go up. The temperature dropping, however, is going to cause the volume to shrink. That's why I have to have the lower temperature on the top. So this should also, you should also try to relate this and approach it logically. It should make sense to you. Make an estimate before you even do the problem. So if you plug in my numbers, here's my initial volume, 4,190. My initial pressure at sea level, 754 divided by 76. Notice I don't necessarily need to convert pressure to atmospheres. I can leave it in millimeters of mercury. I can leave this in liters. The millimeters of mercury is going to cancel out anyway. My ratio of my temperatures is going to cancel. But don't be misled. You cannot plug in Celsius into this temperature, into this equation, because if I plug in negative here into this equation, I get a negative answer. It makes no sense. You have to use the Kelvin scale. Always, always, always. If I plug that in, I get a very, very high volume, 33,800 liters. And that's what I predicted. I said as this balloon rises high into the atmosphere, it's going to greatly increase its volume because pressure is dropping greatly, and that effect is going to greatly outweigh the effect of the lower temperature, which is going to tend to shrink the balloon. This will tend to shrink the balloon. This is going to tend to inflate the balloon, and that greatly overcompensates for this small temperature effect. So you get a very high answer, very large answer. The last law I want to talk about before we go into some problems and some explaining why gases behave as they do, which is called intermolecular forces. I want to talk about what's called Dalton's law of partial pressures. Remember earlier in the video I talked about if you have a mixture of gases, the total pressure inside the container is just equal to the sums of all the pressures of the gases that make up the mixture. That's what Dalton's law says. It's a direct consequence of the kinetic molecular theory. We're assuming that a mixture of gases the gases behave independently. They bounce off each other, but they don't really interact with each other. They don't attract each other. They don't repel each other. They're just there together in the same container, the same vessel, creating the total pressure. If you look at a typical atmospheric pressure, barometric pressure you might call it, it would be made up, most days we are experiencing the pressure due to 5 gases that make up air. Oxygen, which is about 21%, 20.9% to be exact. Nitrogen, which is most air is mostly nitrogen, 78.1%. A little bit of CO2 in the air, 0.033%. That tends to be rising. That's what they're worried about with global warming. The pressure of the humidity, which is pressure of the water, can vary depending on if you're in the summer or winter. And then there's surprisingly a relatively large amount of argon in air. About almost 1% of the air we breathe is argon gas. But that's an illustration of Dalton's law. The reason why, for instance, when you go mountain climbing, why it's hard to breathe, is that the percent of oxygen in the air doesn't change. It's just that the total pressure is lower. Therefore, the amount of the partial pressure of oxygen at high altitude is very low. That's why you need air tanks to breathe. There's not enough oxygen up there. It's not like the percent is going down, but the total pressure is going down. A laboratory application of Dalton's law, if we were doing the lab, this is actually the lab we were going to carry out if we didn't go into the rest of the course being online, would be this situation. When you collect a gas over water, you're using Dalton's law to help you calculate the pressure of the gas that you're collecting. Here's how it works. Let's say you can actually calculate the value of R with this experiment. You can calculate the ideal gas law constant R with this experiment. It's a very simple setup. You take a tube, like a burette or a long tube. You completely fill it with a solution. In this case, we're going to completely fill it with a little bit of acid first. Then we pour in water over that. And we carefully plug it with a cork or rubber stopper that has a piece of magnesium on it. And magnesium reacts with hydrochloric acid very readily. There's an opening in the stopper here. What we do is you got to imagine that this is upside down. We filled it to the top with our acid and water. The acid's sitting at the bottom of the tube. We plug it with our stopper and magnesium. So right now the magnesium is just sitting in water, so it's not going to do anything. No reaction will take place. We quickly invert the tube upside down like this, put it inside a large container of water. We take our finger off the hole that was covering it so it wouldn't leak. And eventually what happens is the acid, being more dense than water, will by gravity fall down to the bottom where it will interact with the magnesium. This reaction takes place. Magnesium plus 2HCl gives you magnesium chloride and hydrogen gas. The hydrogen gas has nowhere to go but up. It's less dense, so it will rise up. It won't come out the tube this way. It will rise up, and it will push the acid solution out. And by how much acid solution is pushed out the opening in this tube, we can measure, we can calculate R. How do we do that? Well, eventually the reaction will stop. The magnesium will all be consumed. This reaction will stop. We'll have all the hydrogen that was formed be trapped up here in the top of the tube with water vapor. Since we collected the gas, it bubbled through, it carried some water molecules with it. So there is some water up here. The gas rises and pushes the excess liquid out. So we measure the volume of the gas, and we know that the pressure inside that container is the atmospheric pressure. The total pressure inside the vessel is equal to the pressure outside. That's atmospheric pressure. If we rearrange that equation, we get this. The pressure of the dry gas that we collected is equal to atmospheric pressure minus the vapor pressure of water, which the vapor pressure of water depends on temperature. The higher the temperature, the higher the vapor pressure of water. So this is an experiment where we would use Dalton's law of partial pressures. That will kind of finish up our discussion of gas laws. I'm going to, we'll have some more videos where we actually do some more homework problems dealing with these problems. But in the next video, part 3, I want to talk about what's called intermolecular forces and explain to you how these forces will be used to predict if something is a solid, liquid, or gas.